So I want to welcome everyone. If this is your first time, my name is Scott Williams. I'm the Research and Education Coordinator at the Wisconsin Energy Institute. And we put on the Sustainable Energy Seminar every other week in the fall and spring to teach students and members of the public about how different disciplines on campus study and develop solutions around sustainable energy challenges. I've got a few logistical things I want to point out. So this seminar is open to the public. For the time being, the public will be viewing online. We have a few students in the room here throughout the rest of the semester. Students in the course are either part of the Certificate in Engineering for Energy Sustainability or the Masters in Sustainable Systems Engineer. We'll continue to do this sort of hybrid format with students in the class and then online and members of the public online until further notice. This session is being recorded. We'll send out a recording. We'll post it on YouTube in the coming weeks. If you want to share it with any friends or colleagues. And I will turn on live captioning for those who would like to enable that feature in Zoom. And if you have questions, please use the Q&A box. I'll be monitoring it from the computer here. But we'll turn it over to our guest speaker today. And if you do have questions, I'll interject or save the questions till the end and address them to our guest speaker today. So our guest speaker is Professor Wang. He's an assistant professor in civil and environmental engineering. And he leads the Sustainable Materials Innovation Lab in the Civil and Environmental Engineering Department. And the lab's mission is to develop innovative and interdisciplinary technological solutions to address the urgent need for sustainable civil engineering materials. So today I'll be talking about some topics related to that for construction materials and how can we decarbonize this sector. So welcome.
All right, thank you, Scott. So if you have trouble hearing me online, please let me know. Just type in chat, let me or Scott know. So let's get started. So I will be talking about embodied carbon emission in construction materials. I just want to start by telling a little bit story. So 4 years ago, before I came to UW-Madison, I was in this Carbon X Prize, which is a competition for like carbon utilization technologies. So as part of that X Prize, I went to visit this town in Wyoming called Gillette. So I don't know how many of you have heard about this city, Gillette, Wyoming. So this is in the middle of Powder River Basin, which at peak supplied more than 60% of the coal to the entire United States. So the town proudly calls itself the energy capital of the nation. So we visited there as part of this competition. So we talked to a bunch of the town folks. They were super nice. All the people there were super nice. And during that visit, we also talked to a lot of energy experts and a lot of politicians. They keep telling us that coal is gonna stay. Coal, we cannot live without coal. And the solution to the coal economy is we're gonna capture CO2 from coal power plants and turn it into something useful. So at the time, I wasn't an expert. I didn't know a lot about energy production. I was doing my research on cementitious material mostly. But when I'm hearing all these things, there were a couple of things that really didn't make sense to me. For one, even though I didn't know a lot about energy at the time, I went to Gillette from California. So in California, we didn't have any coal-fired power plants at the time, and the state was working fine. And also, fracking was booming at the time, so natural gas was super cheap. It's hard for me to envision that coal has to be part of the energy solution. Then the second part that really didn't make sense to me is about turning CO2 into something useful. So that's part of my research. That's why I was there. But because I was doing actual research on it, I recognized just based on the fundamental thermodynamics, it was extremely difficult to turn carbon dioxide into anything that useful and make it economical. But I was standing there listening to the politician talking about how great the coal is, always going to be part of our energy mix, and we're going to solve the solution by turning CO2 into useful product. And all the really nice town folks standing next to me was cheering about everything the politicians were saying. That was the closest experience to being a cop for me. And since then, after I left Jeddah, I paid attention over the years. And I kept an eye on how the coal is doing after the visit. Reality is the coal didn't really get revived. Actually, after it was around 2018. So after 2018, coal continued to decline. It has been declining for a long time, and it continued to decline. And the news out of Jeddah was never great. So looking at these news articles coming out of Jeddah, coal mines being closed down, people losing jobs, but still politicians were claiming we're gonna stick to coal. We're gonna try to find a way to solve this emission issues and make the coal viable again. I just feel bad. Every time I think about that trip, I feel really, really bad. I actually do not know how these politicians and energy experts can sleep at night when they claim all these things. But the point I want to bring out here is that we are looking at some dramatic changes in the next several decades. And most of these changes will be driven by climate change. We know that in order for us to solve our climate change issues, we have to reduce our carbon emissions. And we need to do that pretty fast. So at this point, we're emitting about 35. So this number, they go up and down, depending on how you do the calculation. But at this point, we're emitting about 35 trillion tons of CO2 every year. And if we get our shit together and start reducing emission right away, in order to mitigate climate change impact, limit the impact to a reasonable level, we have to essentially cut our emission to zero by 2050. This is the black line here. So if we continue to drag our feet, continue to increase our emission, and to limit the climate change impact, we have to do it even faster. Essentially, best case scenario, in the next 3 decades, we have to cut all our carbon emission down to zero, everything. And that will drive a lot of dramatic fundamental changes to a lot of communities, a lot of people. They will affect every one of us. So it will be worth to take a look at where the change is going to happen, right? So in some sectors, changes are already happening. So if we look at where our CO2 emissions are from at this point, we know that about a quarter of the emission is from electricity production from power plants, this part. And we know this part, we are seeing changes already. And the changes actually being driven by economics. So at this point, you might already know this, solar and wind electricity is already one of the cheapest way to generate energy. It's cheaper than nuclear, cheaper than coal. That's why coal is now doing very well at this point. I'm not an expert in renewable energies, but there's just one point I want to make here. So, which I don't hear people talk very often. That is, so some people will say, okay, so right now the solar and wind are cheaper because the penetration is limited. If we continue to increase the percentage of energy production from solar and wind, we need to add storage to account for energy storage, so that because we know sun doesn't shine all the time, wind doesn't blow all the time. So that will drive up the cost. That is true, but something people don't often talk about is as you add more wind and solar, the cost for traditional energy production will also go up. So on this graph, maybe the solar and wind cost is underestimated, but the traditional fossil fuel costs for energy production are also underestimated. Because if we have abundant solar and wind electricity, it just doesn't make economic sense to continue to burn coal and natural gas to generate power. During the when sun shines during the midday, and so much cheap electricity coming onto the grid, if you still want to burn coal, which you need to buy, burn natural gas, you're literally losing money. So as we add more solar and wind, the cost for traditional energy production will also go up because you cannot afford to run it all the time. So we will have to see how this continues to work, but in the near term, it's pretty clear our energy transition to renewable is happening pretty fast. And you can see that see the trend in the global power production chart. You see that the renewable energy in the past decades really is picking up. I mean, it's not happening fast enough, but there's no way it's slowing down in the near term. So definitely our electricity power generation sector is getting cleaner. So that a quarter of the pie is getting cleaner. We also know that we generate a lot of CO2 emission from cars and trucks, all the transportation stuff, which is shown here. That's a big part of the pie also. In this sector, transportation, about half is from passenger cars. Then we have trucks, we have airplanes and ships. So we are also seeing changes in this sector as well. So for the passenger car sector, I'm fully confident we will see increasing rate of adoption of electric vehicles, which will drive down the CO2 emission from that. I know this because I personally have been driving the EV for 6-7 years already. So even if I don't care about climate change, I wouldn't even want to go back to a gas car. I hate it. I do not miss going to a gas station. If you ask me what the gas price is, I don't know and I don't care. I don't. And if you talk to a lot of people driving EVs, that's what they will tell you also. So I'm fully confident we can really replace a big part of this sector with EVs. And as we add more renewable energy onto the grid, this transportation will get cleaner. And trucks, I'm also very optimistic. A big portion of this sector will also get cleaner. There are some sectors like airplane and ships, it will be challenging, but it's a relatively smaller percentage in the transportation. Then you can actually see the trend is going. So you see we are on the early stage of acceleration of the EV adoption globally. So I feel very confident about that part. Now, what's left then? If electricity power is getting cleaner, transportation is getting cleaner, what's left? So we have the building energy consumption. These are the building operations, electricity used by the buildings. So as the electricity and the heat production gets cleaner, that part will also get cleaner. I will skip the agriculture section because I have no expertise in that field. So what about this big chunk over here? This is more than a quarter of our total CO2 emission. What is it? So that's the emission we generate to manufacture goods, materials for our day-to-day use. So what are the stuff we are manufacturing that generates so much CO2 emission? So I guess I would just pause a second and ask, what do you think is the largest, the most produced material in the world? What is the most produced material in the world? Concrete. Yes, concrete. That's a good answer. It is concrete. So every year we produce 30 billion tons of concrete. And the next one is cement. So I'm not counting water now. So water probably will be comparable to concrete, but that's a different story. So cement is the next most produced material. We produce at 4 billion tons every year. And the next is steel. We produce it at 1.6 billion tons a year. And anything else is 2 orders magnitude lower than concrete. For example, plastics, 0.3 billion tons. That's 1% of the concrete production. And because we're producing so much materials like concrete and steel, they generate a lot of CO2 emission. And where do we use concrete and steel? It's for construction, buildings, roads, right? So I will talk about where the concrete emission is from. It's really from the production of cement. Cement is used to make concrete. I'll give you some more information. Construction material 101 later. But production of cement itself generates about 7% of our total CO2 emission. So this number goes up and down, depends on how much cement we're producing that year. But on average, it has been about 7%. Steel is another about 7 to 8% of global CO2 emission. So you might think 7 to 8, that doesn't sound like a lot, but let's put this into context. So passenger cars generate about 10% of our CO2 emission. And all the trucks on the road in the entire world generate about 6% of CO2 emission. So the production of cement itself generates more CO2 than all trucks on the road. Of course, there will be a disclaimer here. So in the US, we do not produce that much cement. So in the US, the cement production only accounts for 1% of our total CO2 emission. But globally, cement is a big contributor to the CO2 emission. And another thing I want to it's a side note I want to point out here, is about the scale of the material production. So you notice that other than concrete, everything else we're producing at less than 1 billion tons a year, other than concrete, cement, steel. If you remember, I mentioned that the global CO2 emission at this point is about 35 billion tons. I mentioned that people have thought about converting CO2 into something useful. But if you look at this number, right, if you convert all the plastics in this world, everything, all the plastics, all type of plastics, and you produce plastics only using CO2 captured from the air or from power plants, you're not going to make a dent to the global CO2 emission, right? You produce plastic only from CO2 and assume you don't generate additional CO2 emission during that process. You're only really reducing our global CO2 emission by 1 or 2%. That's it. So that is something we have to keep in mind when we talk about CO2 mitigation. So now we know that this industrial sector, when we're producing this construction material, generates so much CO2 emission, but we're not talking enough about it, right? We talk a lot about converting passenger car trucks to EV. There are tons of startups doing that already, but why are we not talking about enough CO2 emission from cement and steel production? Before we go into details, I just want to do a little bit construction material 101. So what is concrete and cement? So we're going to skip the steel because it's in terms of CO2 emissions, steel production is in a slightly better position than concrete and cement production. So for those of you who don't have a civil engineering background, cement and concrete are different materials. So concrete is the material we use to build our building and roads. So concrete is a mixture of crushed rocks, what we call aggregates. You crush them into different sizes, coarse and fine aggregates. Concrete is a mixture of these crushed rocks, cement, and water, and some minor other things. You mix them together, it will harden over time, and you'll have your building or roads. So essentially, you can think of concrete as man-made rock. Essentially, we take a natural rock, we crush them into these aggregates, then we glue them back together into the shape we want, into buildings, into roads. That's what concrete is. So cement is the glue. Cement we mix with water, it produces glue that hold all these blocks together. So that's what cement is. So concrete, the reason we use so much concrete is really because the ease of construction. The way we make concrete building is we set out some formwork first, just molds for construction. Once you set out formwork, you can either pour concrete into this formwork, or very commonly nowadays for building construction, you pump concrete. So pump concrete, when you just mix them together, mix all the ingredients together, it behaves like liquid. You can actually pump it to several floors high into building, into these formworks. Then you just wait. Once you wait for a day or so, you can take the formwork off, you have your building or you have your concrete structure. So the key benefit of concrete as a construction material is not about its strength, it's not about its mechanical performance, it's not because it's hard, it's not because of anything else. It's because you can form it on the job site. You can take a liquid material, pour into a mold, and shape it into whatever shape you want, and you just wait, and it will harden, give you whatever shape you want. You cannot do that with any other construction material. You cannot actually do that with any material at all at this scale, at the scale we needed to build our building and roads. That is the key benefit of concrete. You cannot shape steel very easily on site. You cannot shape wood very easily into any shape you want at job site either. Only thing you can do that with is concrete. So that makes concrete really indispensable in a lot of construction applications. So you might have heard people are looking into different low carbon footprint construction materials. One of the most talked about material is wood. So you can actually nowadays build tall buildings with timber. If you don't know, the world's tallest timber building is being built in Milwaukee. So if you go to downtown Milwaukee, you can actually see this timber building. It's going to be one of the tallest buildings in the world made of timber, which sounds pretty cool, right? But if you look into it, you'll find this building was built on concrete piles. It's a steel tube filled concrete piles. And the first couple of floors is a concrete parking garage. The building is built on concrete parking garage. So these sections you see over here, these are not made of wood. It's pure concrete, pure concrete. And within this building, within the timber framework, there are two concrete cores. So this is typically how we build high-rise building. You build concrete cores, and which give you buildings the rigidity. So when blow on it, it doesn't topple over. The reason you can do that, you do that with concrete, not with wood or steel, is because when you pour concrete into that formwork, it can form a continuous piece. There's no connection as you add the concrete to it. It's a continual piece of core, rigid core in the middle of the building that can hold your structure very rigidly onto the ground. Then you can build your wood frame or steel frame around it. So you see, even this timber building, we still need concrete. Actually here, the timber is not replacing concrete at all. This is exactly how you would build a steel frame structure with concrete. You will use the same way to use concrete in the steel frame structure like we are doing here. So the timber here is not replacing concrete at all. It's replacing steel. There are applications when you deal with construction, you just cannot get away from concrete. Parking structures, right? When you drive cars a lot, you have to use concrete. You're not going to use wood to build roads, right? We don't use wood to build roads. Yeah, essentially, doesn't matter how you innovate using new materials, it will be really difficult to get away from concrete. So why does concrete production cause so much CO2 emission? So concrete production itself doesn't really generate a lot of CO2 emission because it just you just mix a bunch of stuff, mix rocks, mix cement and water together, you mix them, that's how concrete produced. But cement production generates a lot of CO2 emission. This is because cement production happens at very high temperature. Cement is produced by calcining limestone with some other minerals at very high temperature. So during this production, you generate CO2 from two processes. One is from a chemical reaction. When you burn limestone at high temperature, you drive off CO2 from it. Limestone is made of calcium carbonate. You heat it up at high temperature, it decomposes into lime and CO2. Generates about half of the CO2 emitted from cement production is from that chemical reaction. Then the other half is from burning fossil fuel to get to that high temperature. So overall, when you produce 1 ton cement, you're generating around 0.6 to 0.8 tons of CO2. It used to be almost 1-to-1, but we're increasing our energy efficiency. We're driving down that a little bit over the past decades. Right now, it's like somewhere between 0.6 to 0.8, which is already a big increase. But to further drive down this emission down to zero, it's going to be super difficult. You can take a look at these two components right here. So the chemical reaction, we need this chemical reaction in order to produce cement. Cement is calcium silicate. In order to get that calcium into silicate, you need to drive the CO2 off limestone. Otherwise, you're not going to be able to produce the cement while using them. So as long as you're producing the same cement as we're using now, you have to induce that chemical reaction. Otherwise, you're not going to be able to generate the lime. So it's very difficult to get away from the chemical reaction, CO2 emission, unless we use a new type of cement. Then this high temperature process need us to burn fossil fuel. So I know we have talked about solar and wind. The solar and wind won't be able to generate this high temperature actually. So there's actually no commercial energy technology out there that can really supply this high-grade process heat. So steel actually has the same problem. Steel production also happens at a very high temperature, but steel production is in a slightly better position because when you recycle steel, a lot of our steel, construction steel particularly, are made from recycled steel. When you reproduce recycled steel, reproduce steel from old scrap materials, you could actually use electricity to generate the heat. Cement, on the other hand, it doesn't conduct electricity, so there's generating heat from electricity is not easy. So essentially, at this point, we don't really have a lot of option to reduce this. We don't really have a lot of option to reduce this either. So, and what is the option for cement producers? So in some part of the world, CO2 emission is already being taxed. In California, California has two carbon markets. One is for fuel, mostly for gasoline and other fossil fuels, and the other market is for general carbon markets. Then European also has a carbon market. They gave each company a cap. They tell you you can only emit this much CO2. If you go over that limit, you'll have to go onto this carbon market to buy carbon credit, so you can emit more. So China also just started a national emission trading system earlier last year. So if you look at the average price, by the way, there's actually you can buy investment vehicles that allow you to track the carbon market price now. Overall, the carbon price has been trending trending towards somewhere around $30 a ton. And this price expected to go up as emission policies gets tighter. So as a cement producer, you know that if you produce 1 ton of cement, you're gonna need to emit 0.6, 0.8 tons of CO2. If you cannot deal with that, you can pay the tax in terms of carbon credit. That means every ton of cement, you need to pay about $30 a ton on top of that. And at this point, a ton of cement sells for about $120 a ton. That means the carbon price added to that, you can call it carbon tax, you can call it carbon credit, but you will be essentially adding 25% of your cost. You can either pass that on to customers, you can eat that cost. Eating that cost really isn't an option. And what if this price continues to go up as people expect? It's just going to become infeasible for a cement producer to continue to emit this much CO2. So that's why the Portland Cement Association in the US, Cement Association in the UA, bunch of cement associations around the world have been putting out roadmap towards carbon neutrality. So for example, this is the UK Cement Association. They released a roadmap to carbon neutrality, outlining how they expect to get to carbon neutral by 2050. So they have some really good number here. You see that what they want to do is they're going to use better. They want to use renewable energies that can drive down their CO2 emission by 4%. They use EVs to do transportation that will decrease the carbon intensity by another 7%. They can do use some technology to reduce the what we call low carbon cementation and concrete design, drive down the carbon emission by another 12%. Then use alternative fuels with a low carbon intensity to heat up the cement kiln, that drive down the CO2 emission by another 16%. But the bulk of the CO2 emission they plan to address is through this technology called carbon capture and storage. Essentially, you're going to capture all the carbon emitted from your cement kiln and then put it somewhere. This is not really an innovative cementation technology. Of course, there are some other benefits they want to claim. For example, during the service life of your concrete, the concrete actually reabsorbs some CO2 from the atmosphere. That's what we call carbonation. There's a lot of debate around that, how efficient that is, how much that is. But it's very nice that the UK Cement Association didn't really account for this in their roadmap to carbon neutrality. Although their reduction, 60%, is through this carbon capture and storage technology. Same thing for the European Cement Association's roadmap. You see again, in their roadmap to carbon neutrality, they're counting on carbon capture and storage. There's a lot of innovation they want to claim, but they won't be able to get the cement production down to carbon neutral. So we are still counting on carbon capture and storage. And what is carbon capture storage? So this is now new technology. We have this technology for a long time. Initially, it was developed for power plants. So essentially, you have process that separate CO2 from your power plant or cement manufacturing plant flue gas. You separate the CO2, you concentrate it, you compress it into liquid, you send them through pipeline into some depleted oil and gas reservoir or some other geological formations. You inject it into on the ground, then you seal them off. So that's it. And the cost. So can we do that? Of course we can do that. We have this technology for a long time. This is not new technology. Of course, technologically we can do that, but there's a cost associated. So International Energy Agency estimates the cost for post-combustion capture. This is what we mean by capturing CO2 from cement or power production. The cost is somewhere between $40 to $120 a ton. Based on my anecdotal evidence, the cost is much closer to 120, or even higher than 120 for industrial operations. The $40 ton is really not realistic at all.
That's a question. Is it easier to separate out the CO2 from cement manufacturing compared to, say, coal combustion? Are there other, because coal, there's a lot of other gases and impurities, whereas I'm curious about cements, if that's the case as well.
Yeah, so it's slightly better, mostly because cementitious has one of the highest CO2 concentration among all the industrial flue gases. So in the cementitious flue gas, typically the CO2 concentration is about 20%. In the coal-fired power plants, usually about 12%. Natural gas is about 4%. So less concentrated, more difficult for you to capture. You need more energy. And in terms of impurities, more or less the same. So in coal, nowadays coal power plant all have emission mitigation units that will capture all the sulfur and the nitrous from there. Cement plant also the same. So usually they would over time degrade capture agents. That will definitely go into the cost, but they are more or less the same. Yeah. So again, if you add this to the cost of your cement production, this is no better than paying the CO2 tax at $30 per ton. So people always ask, can you do this? Can you capture CO2? Always the answer is yes, you can capture it, but it just doesn't make sense. It doesn't make sense at this point for cement manufacturer to do it because it will basically double the cost of your cement production. That means everyone who uses cement to make concrete, we're looking at double their material costs. And of course, a lot of other companies are jumping on this bandwagon of capturing CO2. All these old oil gas companies, they have a lot of depleted oil gas reservoir. They want to use this opportunity to make more money. And they are trying to make money basically off cement manufacturers and the coal power plant owners. So they actually do have a strong incentive to do this carbon capture, but the burden will be put on cement manufacturers to eat the cost, or the users who will build the building, build the road, will have to eat the cost, and the cost is really substantial. So then again, you may ask, can we, if it costs so much to put CO2 on the ground, can we use CO2 to make something out of it? Can we make CO2, turn CO2 into concrete? If you, like me, pay attention to these news articles about how to turn CO2 into concrete, you might have seen a lot of articles about that. Turning CO2 into concrete, turning CO2 into that. There are lots of people doing that out there. Before we got too excited, we actually need to do our homework. If you actually do carbon accounting, do accurate carbon accounting, you will find a lot of these processes, they don't make sense at all. They don't make sense at all. So if you do life cycle assessment, do a rigorous life cycle assessment, you will realize a lot of these technology who claim to use CO2 to make concrete actually are now reducing CO2 emissions. They are actually contributing to CO2 emissions. And also, while you are contributing to CO2 emission using these new technologies, you're incurring additional costs to the cement manufacturers, to the concrete manufacturer, to the concrete users. So lastly, I want to introduce Portland Cement Association. That's the cement association in the US. They also just put out a roadmap to carbon neutrality. It's kind of similar to the UK and the European Cement Association's roadmaps, except that they didn't really have a lot of numbers in there. And so I couldn't find a single number to show you actually from the report. But more or less, if we're talking about something similar, you want to use renewable energies. In the midterm, you want to switch to alternative fuels, and in the long term, you do carbon capture. Of course, the whole report really tried to stay away from carbon capture. I understand why they do that, but if I don't think we can do anything better than the UK and the European Cement Association propose. They do mention several other options out there we can adopt, which kind of makes sense. For example, you can replace Portland cement in concrete with the materials we call cementitious, supplementary cementitious materials. These are mostly waste materials like coal ash from coal power plant. These ash, they actually have cementitious properties. You can replace them. You can replace cement with these waste materials that reduce your cement usage and that reduce your carbon footprint. Then you can optimize your concrete design, right? You can try to get the same strength, same performance from the concrete with less cement. If you can do that, you can also reduce your CO2 emission. Again, when you design building, if you don't have to use that much concrete, just don't use that much concrete. That also reduces our overall CO2 emission. So these are really, really good suggestions, but there are two issues. The first thing is the amount of CO2 reduction these practices can achieve are somewhat limited, especially in terms of optimizing concrete design and avoiding over-design. Of course, we can do much better in designing concrete than designing buildings, but there are also other considerations. For example, like I mentioned before, when you build buildings, you are pumping concrete. So if you want concrete to flow like liquid, you have to have enough paste. What I mean by paste is cement plus water. You need to have enough cement, you need to have enough water. You cannot get away with that. Of course, when you pave road, you can get away with that. You can even like having a what we call roller compacted concrete. You can have a roller compacted concrete road that really densifies crushed rocks. So you only need to have so little cement to glue all these rocks together. But that's not a practical solution for buildings. You're not going to be able to put a roller compacted concrete into buildings. And the over design of buildings, we can definitely do better. But how much can we really save that? But the second issue is more important, more interesting to me, is that if you really look at these options, what they are really saying is just use less cement, right? You don't use cement, you use supplementary cementitious material to optimize your concrete design. You use less cement, you use less concrete, you use less cement. These are all really good suggestions, but it's kind of funny that cement manufacturers are telling you, if you want to be cleaner, just use less of our stuff. That's doesn't really induce a lot of optimism on how they can reduce their carbon footprint in the long term. So with that said, there are definitely opportunities for technical innovations in this realm. I can tell you this is going to be super difficult. These cement associations, they are experts in cement chemistry, in concrete design. If they cannot see a clear pathway towards carbon neutrality without carbon capture, this has to be really, really difficult. So overall, there are a couple of ways we can try to drive down the CO2 emission. The first one is, again, improve our cementation efficiency. That's kind of like what we talked about before. You can improve your concrete design. You can find ways to make your cement more effective, so you can use less cement to achieve the same performance. That is something we can work on, and a lot of people are working on that also. And the second way you can do that is recycle or upcycle waste materials as supplementary cementitious material. Again, like I mentioned, cementitious materials are these waste materials that have cementitious properties. But traditionally, we have been only using a small portion of the waste material to replace cement. At this point, we generally replace 20 to 30% of the cement with this supplementary cementitious material, and we only use some particular waste material generated by coal-fired power plants in operation. But coal-fired power plants are closing down. So we can use this as an opportunity to look for other options as cementitious material. So even though the coal power plants are closing down, there are like tons and tons of waste material out there in landfills. So for example, just look at the coal ash. Sure, we're closing down coal-fired power plant, but because we have been burning coal for decades and decades, there are like gigatons of tens of gigatons of coal ash in these old landfill ash ponds. They're just sitting there, sometimes even leaching chemicals or heavy metals into the surrounding communities. So we could actually recycle them, upcycle them as cementitious material to replace them. So this will require some engineering, require a lot of engineering. So we need to figure out how we can select this material, what is the best practice to recycle them, how we can continue consistently supply them without a lot of variation in the performance. This is a common issue for using waste material. Like whenever you're dealing with waste material, the probably varies, depends on what they are, when they are landfilled, all that kind of things. So we need a lot of engineering to make sure we can select, engineer, and use them efficiently in concrete. The last one is, so supplementary cementitious material, they are only one component to cementation. Another key component cementation, which really drives the 50% of the CO2 emission from cement production, is the need to generate lime. So when we do cementation, I'm not going to go into the detail here. One key component is alkaline. We need a base material. It could be either, mostly we have been using calcium hydroxide. We could also use sodium hydroxide or other alkaline, but we need an efficient way to generate this base material. So far, we have been generating this material is calcite. We take either limestone, we calcine it, turn it into lime, that generates calcium hydroxide. For sodium hydroxide, we used to generate also from lime. We generate lime first, then we mix the lime with sodium carbonate that can generate sodium hydroxide. Nowadays, we're doing electrolysis. We electrolyze water, generate sodium hydroxide, which also generates a lot of CO2 emission. So this part needs a lot of scientific breakthrough. We need to find a way to sustainably generate base. Otherwise, none of the other things will really work. So there are two pathways towards sustainable production of base. One is we can utilize available alkaline material that's in the landfill. Some of these wastes, they actually are alkaline. So we can, if we find a way to recycle them, we can generate lime basically for free. Then long-termly, we're probably going to need some kind of electrochemical process to produce lime, produce this base material with the help of renewable electricity that will allow us to sustainably generate cementation without creating a lot of CO2 emission. So this is how I see the whole space gonna move towards. But of course, there are a lot of innovation happening. A lot of people are working on this. So I hope everyone recognizes this is an important issue and keep an eye out for new things that's happening in the field. All right, and that's the end of my presentation. I see a couple of questions online.
Yeah, I'll read out the questions for you so we can all hear. So first question from Raj, and actually I had a similar question. do you think for at least some locations in the US, we could use concentrated solar power for line production? So using renewable energy for a high temperature fuel source? Maybe add geothermal as another opportunity.
So again, I'm not an expert in renewable energy, but my understanding is concentrated solar power, even for power generation, is not economical anymore. CFC is just so much more expensive than solar panels and wind. We are now even building CSP power plants anymore. And if you think about the logistic difficulties in combining a concentrated solar power plant that use so much land with cement production, where we need to concentrate the heat into a cement kiln. There's just a lot of logistic challenges there. I'm sure it can be done, but it's not going to be cheap either. Same for geothermal. If you are living in Iceland, I can definitely say that's the same. If you live near a volcano, for sure. But if you live in most of the US, you're not going to be able to get the high-grade heat from geothermal very easily.
And another question, do you think architectural design of buildings can become an effective tool in optimal minimum use of concrete in buildings?
Yeah, definitely for sure. So if you don't need to use that much concrete, just don't use it. But I would actually have to say that before we can get to that stage, the first thing we do really have to do is do a accurate carbon accounting for all the buildings, all the infrastructure projects. So at this point, our issue is not really with how much concrete we're using, are we over designing it? The key issue that's preventing us from doing this is actually we don't even know how much carbon we're generating in our building or infrastructure project for most of the projects. So most people, when we build a new infrastructure project, new building, we're not doing any kind of carbon accounting. We do not know how much CO2 emission is being generated for the construction material we're using to build this project. So without doing that, how can we actually reduce our carbon emission? So we have to do this first step first to make sure we have an accurate, consistent way to do carbon accounting. So I really want to emphasize this is like a very, very important issue. Without doing this, we cannot really do anything else.
Another question, are there known health co-benefits or issues with the alternatives that are presented, maybe some of the innovations?
Yeah, so actually, when you recycle this waste material into concrete, you're more or less encasing them into a solid material. You're reducing the environmental issues with the leaching of heavy metals or whatever. People have actually done a lot of study on this. When you, if you leave these coal ash in landfills and you have water running through them, you are risking of leaching a lot of these heavy metal or other compounds that could have health impact. But if you recycle them into concrete, it actually reduces that environmental benefit. So there's actually a lot of benefit to recycle these materials into concrete.
Another question online. As the climate gets warmer, do you think it'll make a difference in emissions from building materials?
Good question. That's very interesting. That's definitely beyond my expertise. Well, that we need a very complicated, very thorough environmental analysis for all the building projects and coupling with the climate. But one thing I know for sure is, if we do not control our climate change issue, we will have to upgrade our infrastructure, right? If you look at around the coast, up and down East Coast, West Coast, people are building more sea walls, building taller sea walls. Army Corps engineer recently said we need to build 20-foot tall sea wall to around Miami to deal with the sea level rise. So if we do not control our climate change, one thing I know for sure is we're going to need to use more concrete. We're going to need to upgrade our infrastructure. We're going to need to raise the road. We need to build sea walls, build all the things. That will drive up our use of concrete. This is just a pretty vicious cycle, for sure.
Yeah, you can see more roads washing out or other issues of having to repair roads more frequently.
Yeah.
Let's see. The question here, given the challenges of decarbonizing concrete, are there any alternatives to cement or concrete that have the same formability advantages?
At this point, unfortunately, no, we don't have any materials. So when we talk about innovation in construction materials, people always say that we love innovations as long as it doesn't drive up the cost by 1 cent a pound. Right? There are materials out there that has better mechanical performance. There are better workability. You can find glues. If you want to glue stuff together, you don't have to actually use cement. If you want to glue stuff, you can buy really strong glue from Home Depot that can glue it still together, like super very high strength. But it just doesn't make sense. We cannot produce them at large enough quantity that can satisfy our needs for building buildings and roads, right? We have to consider that as part of this consideration. There are better materials. There are definitely better materials in almost any way compared to concrete. There are better materials in terms of mechanical performance, chemical durability, anything you can think of, there are better materials. But can we produce them at this scale, 30 gigaton a year? That's the question.
Any questions for Marty?
Yeah, that's definitely one option people are looking into. So when we talk about hybrid heat for steel or concrete production or any kind of heat, you need to go up to temperature of over 800. There are no other options at this point other than fossil fuel. The only options people are thinking about is either hydrogen or ammonia. These are the two. Ammonia is basically the same, it's just hydrogen. When you burn ammonia, it's basically burning hydrogen. But other than this, we don't have any option. I should say that maybe nuclear power is another option. I know people are looking into that. If you can develop a small modular nuclear unit, it generates tons of heat that can power all this production. So there are a lot of, there are definitely technologies that have the possibility of powering these processes. But at this point, there's no commercially available technology, even hydrogen. There's no commercial hydrogen driven cement production at this point.
And then maybe one more question. Have 3D printed homes become a viable solution?
That's interesting. So in theory, it would. That actually goes to the first one, improve cementation efficiency, right? So if you don't need to have concrete in all part of your structure, you can leave lots of holes, hollow spaces in it. You would reduce a lot of concrete usage and reduce the associated CO2 emissions. So 3D printing, in theory, can do that. It will allow you to use material a lot smarter than we are doing that. But the downside is the technology, again, is not there. There are a lot of other challenges associated with 3D printing. I can't go into detail right now, but I can talk more about that if you're interested. Send me an email. But if you look, you can go on YouTube and look for some of these startups that are 3D print homes. You'll notice what they're really doing is 3D printing walls. That's the least challenging structural component you can think of. If you can do 3D printing and you only print walls, there's something wrong with your technology. That means you're not doing really 3D printing. When you build a building, walls are like the least challenging part of your construction. So at this point, it's very challenging for concrete 3D printing to print overhead. So what I mean overhead is you print a structure that has a slope and it actually tilts. A wall is not straight up. Wall is kind of tilted wall. So no company out there, startup company, can actually 3D print that. What that means is their technology is no better than traditional pour into the form custom place concrete at this point. So hopefully we will find a way to address these technical challenges. And once we are able to create these overhangs, we can print all kinds of complicated geometries that will really, really drive the benefits of the 3D printing. At this point, the technology we have right now, there's not much benefit at all.
I think we're out of time, but thank you so much for your presentation, and it was very informative. Thanks so much.
All right, thank you, everyone. Bye.
Thanks everyone for joining us online. Come back in 2 weeks.